Okay, so yeah, the presentation is going to be done. Both myself and Whitney will do part of the presentation. So just a quick introduction. My name is Ettore Tiotto. I work for IBM, and I work in the IBM Excel compiler team. And Whitney is also my colleague. She also works in the same team for the Excel C++ and also Fortran compiler. So the talk today is going to be a little bit different from what we have seen before. It's going to be centric about loop optimization and how our experience in trying to enhance and adapt the LLVM existing loop optimization infrastructure for certain interesting application that we have an interest in optimizing well. Stand for the fact in February, IBM, we have announced that we are increasingly adopting the LLVM open source infrastructure in our own commercial compilers. And that goes beyond just C++. So to say, our focus, we have a very strong history in providing optimized Fortran compilers. So we're also migrating our entire offering for C++ and Fortran to use the LLVM optimizers. And we're trying to do it across all platforms that we support. So for Linux power and also for RX and iOS and even for ZOS. So today, what I want to share with you is our experience practical experience in analyzing the performance of a couple of application kernels. And since we do support a Fortran compiler, the first one that I'm going to talk about is a particularly interesting Fortran kernel, where there is a hot loop that we're going to see how to optimize and what we have done within the LLVM infrastructure to get performance improvement. And then the second part of the talk is going to be over to Whitney, and she's going to focus on K-means algorithm written as a C kernel. And we're going to then discuss a little bit about our future plans and future works and what we plan to do for the rest of this year and moving forward. So the first thing I want to talk about is this particular application. This is written in Fortran, and the profile is pretty good because he has a very hot function that takes about half or even more than half of the execution time of the entire application. And then, there is another function that is also pretty hot, and, there is probably four functions that takes the entire profile. In this talk, we're going to focus specifically on the topmost function, the one that is hottest. And that function contains one loop where we spend essentially most of the time spent inside that loop. Simplified, the loop looks pretty much like this. It's a five-dimensional file-level loop nest. It's written in Fortran. It accesses a number of arrays, and there is a number of multiplication and addition. So what I want to observe here is that because of the property of the language, all these arrays, A, B, C, and so on, are disjoint in memory. So they don't overlap, and we can consider them as they were, restricted pointer. They're not alias to each other. And that makes the work of figuring out the dependence analysis, the access pattern easier for the compiler. And that's often true for a lot of Fortran applications. So, like I said, we spend about 0.5% of the time and essentially all the time in this function inside this loop. And so the issues that we're looking at is L1 cache misses. So what I have highlighted on the slides is all these arrays, they have 5 indexes, and the fastest moving index is in Fortran is the leftmost index, so the one with index L. And if we start to analyze the access pattern in memory for each one of these arrays, we notice that the access pattern is threaded. The reason for it is that the fastest moving index is L, but the loop with the induction variable L is not the innermost loop. So the access the jumping memory by the size of the loop by NL. Okay, so what can we do about to improve, to remove the L1 cache accessing process? So every time that we access one of these array element, we're gonna get a cache miss, and then bring in a cache line, and then essentially utilize only 4 8 bytes. I don't remember if this is a float or real 8 or real 4 element size. Essentially only use a very small portion of the cache line, and then jump to the, get the next access, and the next is gonna also cache miss and so on. So it's very pure L1 cache utilization. The typical compiler transformation that helps in this case is loop interchange. And loop interchange is a very is a transformation that will do a permutation of the loop iteration space. In this case, what's needed is to interchange the loop L and M with each other to associate so that these array the access memory in stride one fashion, and that gives good cache locality and reuse. And if we do that, then the access pattern looks great, and we're going to get rid of, we're going to use the cache, the L1 cache efficiently. So that was the issue that we had to solve, optimize this hot kernel and doing within LLVM, and then build kind of like the infrastructure to be able to accomplish that in our own compiler. So to interchange loops, of course, we need to prove that the loops, it is legal to do so. And so we need to prove, the data dependency are preserved after the interchange move. And for that, it was very encouraging because we were able to use the existing LLVM data dependencies analysis, almost unmodified, with a few extra information from the training into the IR. Essentially, the front end is going to tell us that these arrays are all disjoint, and they are the pointers are all restricted pointers, and even that all the accesses are inbound. So proving dependencies it was not proving legality was not really an issue for this kernel. The challenge was more toward figuring out what to do, like when it is profitable to interchange the two loops based on the consideration of cache misses and the amount of cache line that each loop nest configuration would use. So we have created an analysis based on known papers from, the subject matter area is very well known. So we actually have not created an analysis, we've implemented an analysis within the LLVM compiler. And this analysis is able to determine the number of cache lines that are used by the body of the loop whenever each one of these loops is in the innermost position in the nest. And then it provides that information, right? So the last bullet here is about more the interchange mechanics. So loop interchange existed already in LLVM, but we have slightly adapted it to one use this new analysis, and the other to operate more easily on perfect loop nests, because essentially the mechanics of the transformation are much easier if the loop nest is perfect. And to create a perfect loop nest, we introduce a transformation called loop fission or loop distribution, which is also very well known in the compiler literature. And for our own purpose, this nest, we wanted to make it a perfect loop nest. So it wasn't perfect because there is a statement, an initialization statement for the array Y between the loop L and the loop M. And so we wanted to kind of distribute that away to make the resulting loop nest perfect. And that's what loop fission does. It will distribute that array in its own 4-dimensional loop nest. And then the remaining loop nest is perfect. Actually, both loop nests are perfect. As a side effect, we also kind of expose our memset opportunity, because the entire 4-dimensional loop nest can then be summarized into just a call to memset. But the focus would have been that's you know, like side effect, and then the focus more in the lower loop. So once the loop nest is perfect, our analysis would kick in and start to, you know, detect all the cache, all the number of cache line that each one of these array in the loop nest consumes, and then annotate each one of the loops with the cost. The cost is essentially an estimation of the cache footprint for that loop, if that loop was in the innermost position in the nest. The printout that I have over there on cache cost is actually coming from the tracing information that we have in the optimizer, and it prints out that, you know, the I loop consumed, if it was moved in the innermost position of the nest, that would be a very bad idea, because it consumes a lot of cache lines. And then, you know, the J loop and the K loop and so on. And then I want to point your attention to the last two, the one that I marked in orange and in blue. So the M loop has consumed more cache line than the L loop. And so that gives us the information to figure out that it would be profitable to move the L loop into the innermost position in the nest. And essentially, that vector gives you the optimal permutation of the loop iteration space to reduce the number of cache misses. After hooking up that to loop interchange, we go through the information, and then it will check for profitability, find out that there is, and then try to figure out the minimum set of permutation move, or, you know, pair exchanges of the loops to bring the loop in the optimal configuration. In this particular case, the number of moves is only one, exchange L and N. So here is a little bit of, you know, what's the effect in the performance of this Fortran loop and the application for you know, after doing the loop fission and the interchange. So for completeness, I have the throughput, so the number of, you know, essentially number of memory accesses that were not. So the scale is proportional to the number of memory access, the throughput of the bench. So higher is better. At O3 or 3 LTO, the throughput is on the left, the original, and then interchange, we can see that we have almost a 2x improvement due to this transformation that allows us to eliminate the cache misses, the L1 cache misses. Contribution for this work that we have done is that, you know, the main contribution has been the new analysis we have upstream, and that's available in the LLVM trunk. And so the other contribution that we have here is loop fission, is a transformation that we are currently still working on. Our intent is to have a powerful, different kind of heuristic for loop fission. I showed you one, the simplest one, essentially to try to, you know, distribute to create a loop that's perfect, so that downstream optimization can make use of that and they become simpler. But loop fission is a much more generic type of transformation that can, for example, reduce the register pressure in loop. It can reduce the number of hardware streams that a loop is consuming if there are too many hardware streams, and do other interesting things. And our loop distribution for LLVM is really being written for vectorization. So essentially, if there is a loop where some statement they have some loop carry dependency that would prevent vectorization of the loop nest as is, what loop fission does today in LLVM is try to distribute those statements into a separate loop nest so that the remaining loop can then be vectorized. You know, and last and but not least is the the ability to do interchanging throughout, for an interloop nest by using a different kind of heuristic for cache analysis. So that's the end of my portion of the presentation. Next, Whitney is going to discuss the second case study, which is k-means.
Thanks, Ettore. Can everyone hear me well?
Hear you.
Okay, good. So for the second case study, we're going to cover a well-known, quite popular algorithm, namely k-means. K-means partition data set into k predefined clusters. And in this version of k-means, the hottest pattern of the code is actually two side-by-side call instruction, where the first call calls to a function called normalize, and then second call calls to a function called dot product. And below is the two definition of the two function, where normalize, it takes in an input v2, array input v2, and then it updates all its element by dividing it with r bar. And the second function dot product do exactly how it named. It takes in two arrays, v1 and v2, and do a dot product of them. Given that the hottest pattern that takes most of the time of the kernel is two function calls, or a repeat of this pattern of these two function calls, it makes sense to first look at inlining, because inlining can reduce the call overhead, and also more importantly, it can increase the scope for future function optimization. So on the left-hand side is the code we saw exactly the same as the previous slide, and on the right-hand side is what it will look like after inlining. Inlining by itself can give this kernel a 13% improvement. And now we have two loops. We can see that the two loops have exactly the same bound, and they happen to be side by side. So it's a good candidate for a loop fusion. Loop fusion is a transformation that fuse two or more loops into a smaller number of loops, where in this case we have two loops and it fuses into one loop that I mark it in green, where the first statement is from the first loop and the second statement is from the second loop. There's many benefits from doing loop fusion. There's the direct portion and the indirect portion. Directly, it helps increase the data reuse. It also reduces the loop overhead. And by doing loop fusion, we can see a 5% improvement on k-means. And the indirect part is it increases the scope for loop optimization and also enable later transformation. And it will be one of the critical things for this case study. After the loop being fused, we can see that there is mostly accessing of the array v2 element I, where first we load it and then we do a division and we store the value to v2 sub I again, and we load it again. So as we are loading v2 sub I just right after the store, we already know what the values is stored in v2 sub I because we just stole it. So there's no need to do the load, and we can just directly use the value that we stole earlier. And this is this is called Merm to rag in LLVM. It is a utility that can be called by different passes, and there's more than one pass doing this transformation, where one of them is promote pass, which do exactly that, and there's another example is SROA for scalar replacement of aggregate. I didn't have a percentage gain for this one because this transformation is very fundamental, and if I don't do it, it will take forever to compile. And the final pass that I'm going to cover for this case study is the desktop elimination, DSE in short. After the second loop being illuminated, and also the observation that the array V2 is either fully overwritten after the loop or before the next load, or there is no more use of this array. So the stall to V2 sub I can be safely eliminated is that if we are able to do this, this will give us another more than 15% gain. Notice that this stall is only that after loop fusion. If loop fusion didn't happen, the second loop will still have a load to V2 sub I, and this stall cannot be safely eliminated. With all that together, here is a picture of what's the performance gain from the current LLVM-03 pipeline. We're using the new pass manager. Because inlining already happened in 03, so that's why it is below the 0 baseline. And then on top of 03, we get a 5% gain from loop fusion and another more than 15% gain from desktop elimination, which give us more than 20% gain. Here's the current status of the transformation I cover for case study 2, where they are inliner, loop fuse, and promote, and DSC. All of them already have our implementation in the LLVM code base. And the top 3 of them actually already able to handle the case that I just described for k-means. And the only one that need to do some further enhancement is desktop elimination. And community is actively working on enhancing desktop elimination. And the main 2 reasons that currently is not catching the opportunity already have Facilla items, and the details can be viewed there, which is 46458 and 46460. With that 2 main concern feature implement, the desktop elimination should be able to cover the case described as well. Loop fusion is actually was initially contributed by IBM and ANL. In fact, it is the very first transformation IBM worked on in OP. Throughout the year, patches and enhancement have been added for loop fusion, which one of the example is to handle intervening code, meaning if I have 2 loops I want to fuse, and if there is some code in between and it's safe to be moved before or after the 2 loops, we will try to do so instead of just bailing out and say loop fusion doesn't support it. Another example that we have been trying to actively work on is loop peeling. Is if the 2 candidate loops for fusion have different loop iterations count, instead of, again, currently we'll say cannot fuse, we'll try to peel the exceed iteration and do the fusion when profitable. The biggest problem with loop fusion, though, is it is currently not enabled or not even added into the LLVM pipeline. Because before doing that, we have to answer the question of the placement of loop fusion in the pipeline. Where should we put it? That's why this case study can somewhat help answer this question. We know from this case study that it would be better if loop fusion is added after inlining, but before transformation like desktop elimination. We will still need to do more case study to have a better idea on where to put loop fusion. But in this case study, we know that loop fusion is a very good enabler for later on transformation, so it's good to put early. Here is a list of works that need to be done if we want to have the improvement that we mentioned for the 2 case study. One is a new transformation that is needed called loop fission to distribute the loops where paired with an analysis called fission interference graph, which we have a fabricator review. It is used to balance different factors, for example, register pressure, number of streams, factorization opportunity, or the creating perfectness as described it by Ettore. And next is we need to add loop fusion to the pipeline, and finally some improvement need to be done on some existing transformation, for example, that called elimination and loop interchange. Conclusion. LLVM loop optimization infrastructure can be successfully enhanced to optimize representative loops from HPC application from different vendors. We have illustrated this with two kernels, one from C and one for written in Fortran, where they get 2x and 20% improvement respectively. IBM is actively contributing to LLVM community in several ways. First is the one we mainly cover in this talk, the loop optimization technology. And before that, the first thing that we contribute was actually the PowerPC code generation in LLC. And on top of that is adding support for some new platform for LLVM, for example, AIX, and the recently announced new platform of COS. Thank you, and if there's any question.
Thank you very much.